Ladies and gentlemen, it's my pleasure to chair this afternoon session. My name is Peter Slootman, University of Amsterdam, and from NTU. And it's my pleasure to introduce the next speaker. Chris and myself, we go a long way, I guess. We met first in 1995 in Santa Fe, which seems to be like a center of place where everybody meets everybody. And Chris was at that time at Los Alamos National Laboratory in the theoretical physics group, working on epidemics models. And I think he was really one of the first people taking into account social behavior, mobility, and things like that, in addition to, let's say, virological information. I think it was really a breakthrough in doing these kind of models. Later on, we met again in Stockholm, where Chris was doing his sabbatical somewhere, I don't know, remember, but somewhere around, what must have been, like 2000 or so. 96. Yeah, okay, close enough. And I was actually very lucky that he was willing to accept coming to Singapore a couple of months ago when we did our International Conference on Computational Science here. And so this is the second time in this year that Chris is here. And he will be talking about globalized decision informatics. You know, the thing is with introducing people which are already pretty famous, you always say this person doesn't need any introduction, and then you go at length giving them an introduction, which I'm not going to do because his bio is pretty complete and pretty comprehensive, I would say. So feel free to read that, and in the meantime, I would like to give the floor to Chris.
Use this microphone. So by globalized decision informatics, what I'm going to try and do here is the impression is to defeat an impression that I've managed to leave, and the people that I've worked with over the years have managed to leave, that we make models, because we of course make models, but the real goal is to support decision makers. And with socially coupled systems, especially for the kinds of problems that we've talked about today and that I'll talk about in here, you really have to embed these systems in the social process itself. Otherwise, they don't really, the people using the system are part of the system in a very direct and important way. This isn't a kind of science where you can be quite so abstracted. It makes the nuts and bolts of putting these things together hard. I mean, for 25 years, we've been trying to get these things to scale, run fast, be distributed over the web, overcome communication delays, all kinds of things. And what's starting to happen is pretty remarkable. So I'm not going to talk about modeling so much as issues, and really exciting, I think, issues in decision informatics that I hope maybe be a little provocative and maybe generate some collaboration going forward. I hope so. So the bottom line really is, I am something of a tool maker. That's what we do. It's what my lab has done. I want to point out something about my lab before I go forward. This lab has many different kinds of people in it. So we have economists, we have physicists, mathematicians, computer scientists, programmers, public health people, biologists. But either they work on this platform, or they use the platform, or they don't do it in our laboratory. So this platform, which I'll describe a little bit as we go forward, is a synthetic information environment that supports a broad range of things that are interactionist, and we'll talk about that. And in particular, what we're really interested in a lot is socially coupled systems. There's 75 people in this lab right now. A couple of years are probably close to 100, and I hope it stops around there. But we've been doing this a long time. So this isn't my work. This is work of many people, and I just wanted to, this isn't something I'm not this energetic to do this alone. Okay, so we want to incorporate many interdependent stakeholders and systems. What does many mean? Well, it certainly means something more than one decision maker, whatever that means, one policy maker. It means large numbers, up to and including, in epidemiological models, public health models, for example, parents that decide or don't decide to send their children to school are stakeholders. And they make decisions, and if you give them information and they can make known to you what they're doing, you could have, in other words, millions of stakeholders in these kinds of systems. That would be fair. Usually we don't. Usually we have tens to hundreds of stakeholders. Coevolution, these systems branch, and I'll talk about coevolution in a single example, but coevolution, if you think of these things as networks, you have multiple networks and they co-evolve. Something happens in one, it changes the other one, it doesn't do what it would have done if you hadn't done what you did. This is a really important aspect because the systems branch. It has a lot to say about how you study them, and certainly how you simulate them, certainly how you make decisions about them also. The distributed knowledge and actions comes along with this. The path dependencies are what are driven by this. And what we need then, because of these things, and I can say this from a very formal point of view, or it's a common sense if you think of it this way, these systems change when people act. So they go on paths, and they're very path dependent. It is simply impossible to calculate the full range of possible behavior of these systems in the kind of detail that I'm going to be talking about. So you need what I call, a little pejoratively, I guess, muddle through systems, or incremental systems, or iterative systems, where you decide and the systems change and you just stay inside the system and you follow the system forward and you use the system to help you understand what to do next. And there's a lot of foundational research that goes in here, mathematical research, theoretical computer science, and the real question at some point, it comes up like, why do you need that? And we'll talk a little bit about that, not too much. And lastly, to get this coupled, you really do need pervasive deployment schemes and strategies. That's one of the reasons it has to scale. It has to run in web-based and other sort of pervasive push-style forms. And it's the reason that I called it globalized. At the end, I'll talk about some grand challenge kinds of problems. So at the end of the day, like I said, I'm not an economist. I'm not a traffic engineer. I'm not an epidemiologist. Apparently, I'm not a mechanical engineer either. And I'm a tool maker, but I'm not. So, complex system models. So the first thing I'd like to talk about is, so for a long time, we've been working on highly scalable models. The numbers we work with now are, we almost never compute anything that's less than 1 million interacting entities. We are normally computing between 10 to the 7th and 10 to the 9th interacting entities now. It sounds like a lot, but it just happens that way. But we mean by complex systems in this regard, at the level of individuals in an area, when we get individuals and we know each of these individuals, the details of what they do that are relevant to whatever kinds of behavior we're talking about. And at the level of household here, you see a mother and a child. They do different things during the day. They come in contact with different people during the day. They generate contact networks that you can extract. But there's also lots of other things going on. And so complex systems mean those kinds of interactions, but also all these interactions among things like infrastructures and components of infrastructures and all those kinds of things. And that's the reason you get up to so many interacting pieces if you want to study these things in the kind of environments I'm talking about. So this is an old slide, but it makes the point that to understand how power networks work, usually the population is a giant resistor, and you have generators and distribution schemes, and the population is a giant resistor, and it may vary by time of day or something, but we actually do demand-side modeling in a lot of detail, and we have mesoscopic modeling as well, in that we generate things like bilateral contract markets. And it turns out that you really can't understand even the short-term operation of the allocation of power over the network without understanding how the power economics works. But you certainly can't understand the longer term economics. There are things like market power by position, geographical position, and many other things that are really only come to light if you put these things in. And so that interacts. It interacts with infrastructure capacity over time. It changes, but it's also connected to the transport system and communication system and the public health system and a lot of other things. And depending on how this works, you change contact structures and so on. So this is the kind of thing that you start building up into. These kinds of systems, they have to scale to these sorts of sizes and stuff. It isn't like you just stick models together. These are not federations of models that you're trying to, make a point prediction on exactly what's going to happen. It's a bit different than that. I'll sort of describe how this goes. They have to be able to scale both in spatially and in speed, and they have to be used, or they actually don't exist because there's no other way to really get information into them. A lot of there's some information you can get from a survey, like the census or a travel survey or something, but there's other kind of information that you need that comes from, for example, what questions are being asked of the system. You have to use it or you don't get those questions. And it turns out that even though you may have a public health person, a Department of Defense person, and somebody worrying about transportation systems, it turns out that they may have a very interesting conjunction of interests, but you don't know that if they're not using the system. So you have to stay inside decision loops in these kinds of systems. I'm sorry for this tedious stuff. I'll try and move past this a little bit, but the topic is globalization of these systems, so this is stuff that matters to them. 7 years ago, I left Los Alamos. We lived through the generation of high-performance machines from really fairly exotic things to fairly routinely available things. And about the time we got here, if you ran a fairly detailed model, a very detailed model actually, of something the size of metropolitan Los Angeles or metropolitan San Francisco or someplace like that, approximately 10 million people over a large geographical area, and you're talking about every person, the details of their mobility, and depending on a few other things, some other stuff, some certain kinds of economic decisions and other things. It would take us to run, if we put an epidemic on that system, it would take about 48 hours to run a 200-day, epidemic cycle on that. So to do 200 days, it takes about 48 hours, and then we did it on patches of these machines, so you could run several different replicates. In principle, it would take us a week or two to do a very large, study, and we had to do the study, and so on. Right now, they're running in about 45 seconds on roughly the same machines because the representational techniques have improved, and the way we handle. We don't run off files anymore. We have data library methods to connect these representations. But we're now looking at changing machines, and we a lot more seriously than we have for about 10 years. And we expect in I say 5 years because I know in 5 years this is going to be true, but in a couple of years we think we'll be doing this in a half a second. Moore's law isn't causing this to happen. I'd say that what we're doing is causing Moore's law more like to happen. And we've also changed, and much more importantly, is once this happens, once you get to 45 seconds, the things you have to do to make it possible that we don't run their studies for them anymore. They run their own studies. We make interfaces, and we serve these things over the web. And by they, I mean staff epidemiologists, say, at BARDA or ASPR in DHHS, in the Health and Human Services in the United States, or in one of the Department of Defense organizations that's worried about the health of forces or something. These people are running these studies themselves. And so there's many things that have changed about the accessibility in the last 6 or 7 years. I said there's 10 to 9th interacting agents. This is totally suppressed at the level of epidemiologists. By working with them, we give them an interface that allows them to ask the questions that they need to ask. That's what their interface gives them. They do not do all the stuff necessary to set these systems up. It doesn't mean that the system doesn't have to do some pretty fancy stuff to be able to react to what they ask, but it does mean that we constrain the system to be available to them in a way they understand. And that's so that they will use it for all the reasons I talked about. The synthetic resources that they use, for example, if you're talking about people in the Medical Command in the Department of Defense and the CDC and some other places, public health officials in local areas and so on, they don't necessarily talk to one another, but if they're jointly or even accidentally commonly using this platform, and if the information that they're generating is being left behind in one form or another, either the synthetic populations or the activity structures or dendrograms or whatever it is about certain areas, it turns out that as questions are asked in certain contexts, which are semantic contexts, constructs that are intentional, as the intention of the system moves, the system follows fads and trends and operates faster when you're inside of one than when you're outside of one, for example, which is kind of interesting and offers a potential forward pointer for a lot of really interesting work. And so participative information uptake and use like mass decision making and crowdsourcing fits naturally into these user communities. In fact, sometimes you're getting information uptake participatively simply by monitoring the metadata associated with their questions. So probably you see the little green guys running around there? So that's Washington, D.C. This is sort of the current state of some technology that we started called Transims. We started this in 1990, I think. It went for a long time. Every one of those cars, you can go into the data structures associated with them. You can find out who's in there, what they're doing. The traffic is generating traffic jams and stuff, so you can figure out if they're late or not. This is a single realization. You don't really, this is just so people understand what's going on in there. You normally wouldn't present things this way, but that's the level of detail at the level of traffic that goes on. This is once a second and about 5 meters in spatial resolution. When they turn on radios, like cell phones, and they move in traffic, this is in a certain band. These are the interference networks associated with competition for in-band frequency. Depending on the protocols for your cell phone and stuff. This is important, and it turns out then that the capacity of this system is influenced by the mobility patterns of the vehicles. This is an hour-by-hour aggregate, but it's going on in 5-second updates or 15-second updates. But this is demand-side, individual by individual demand-side calculation of electrical power demand. And this is what replaces the resistor, part of what replaces the resistor. And this is kind of interesting. The shaded area this is an interdependency example. These are just examples of what we mean by complex systems. They're complex for a lot of different reasons. You know, the traffic models, all these things that you do, even deciding whether you're going to walk or take the train or drive or bicycle or something, get picked up. Those are interdependencies. People interact in traffic. There's lots of interdependencies. Household members share transport. Those are all interdependencies. That's pretty complex, I guess. We have to do that. But here, in that area there was an event, and it caused a shutdown of electrical power in that area. So it turned off the light of the traffic lights and also disenabled trams. And so, you see the red up there in that area is traffic congestion starts to build up as people's plans are unable to be satisfied by their mobility is unable to be satisfied by the system because of loss of traffic control. But you see in the lower left, it's weird that it's a long, complicated story, but you get traffic congestion down there too. So if this event happened because of a natural disaster or man-made disaster, from an evacuation point of view, you might not realize that you really shouldn't evacuate through that area down there. But you can realize it because you have these kinds of interactive studies. And you can go back in and figure out why. These are causal representations, and you can go back in and figure out why. Now, these aren't point predictions, but what they do tell you is they tell you what the dependencies are between things. So you set these things up not as a single run, you set them up as experiments. You set them up like sparsely sampled, like experiments, like experimental design. So these interfaces replace the concept of setting up a single prediction with the process of doing factorial style sparse designs and understanding them. Similarly, as folks are driving around and getting next to base stations, you can calculate what the load on the base stations would be. And you don't just know the load, you know what they're using. So this is a different kind of complexity, and I don't have a little dancing movie because I couldn't figure out how to make a movie out of the data. But if you have an earthquake or a bomb or, I don't know, something that happens, and you have somebody that survives it named Fred, there on the left. Well, at the point of that event, you don't just need to know where Fred was, you need to know that Fred's household, for example, or workplace, depends on the situation, but in this case, household, they were in certain places at the time of that event as well. And not to put too fine a point on this, because this is a matter of a certain amount of research, social research, the behavioral models associated with what Fred is probably going to do and how he's going to interact with certain kinds of policies intended to help Fred and everybody else. The fact, though, is if he doesn't have communication, he can't verify where these other people are, it's unlikely that he's going to do much to comply with what you want him to do other than go find his household. Or to go home. There's lots of examples of that. In Fukushima, people walked 36 hours. In New York, people walked at 9/11, people walked 24 hours. They really did walk that long, and they walked home, basically. But this can also, so you can calculate what the migration pathways are, and you can figure out where things like decontamination stations or medical support or evacuation routes, where things would be affected. So you can make, if you want to, you can make an evacuation plan. It can be a policy. You can tell people to do it. But if you don't understand how it's going to interact with what people's behavioral tendencies are, you're not going to get anything remotely like any kind of understanding of what the policy is like. So this is a complex issue. This is an issue where this will eventually be a plume that arises, like a toxic plume it could be. This particular case, it's a nothing plume, but it's a real complicated plume calculation in the urban terrain. There's atmospheric modeling going on, air chemistry modeling going on. And you get a plume. It covers things, and so the obvious thing to do then, if you want to understand mobility, and I mean if you want to understand exposures, is that once you have the plume, then you can figure out what the exposures would be like, and that obviously is going to change by, time of year and time of day and all kinds of things. Amount of information available, whether they know it's there or not. This is the red and green things are spatially represented distributions of disease in the population of Alabama. That's 4.5 million people. This is one of the cities. Just to show the resolution of the sort of analysis you can do. This is in a neighborhood. And the blue dots, after having run this a couple thousand times, with overwhelming likelihood, people in the houses marked by the blue dots got picked up in the epidemic, and the ones in the houses that were not marked did not. And so the question then is, can you figure out, why? So one of the more standard things is they normally are related to school children, but there can be lots of reasons for this. The point is that the macroscopic model in this one, very much like the micro to macro stuff in economic reasoning, happens here. In fact, this is a case where we put a coevolving economic model in a contagion model, and it had to do with understanding the distribution of antivirals in a population during an epidemic. The problem is that you're going to distribute, you have about 15% coverage of the population in an antiviral stockpile. You don't have everybody having antivirals, and you want to know who to give it to maximally affect the attack rate of the disease. And so in the United States, there's I'll call them originalists, perspective on things that say that they don't believe that the government really can figure this out. And they may be right. I mean, I don't think anybody's figured it out. But the point is that they don't like that. They want the market to distribute these things. Well, I mean, if you just sell stuff like this, it's going to be automatically really regressive, and you don't really need to do the analysis to know what's going to happen. With antivirals, I just want to point out that this is the scope of the problem. Well, this is part of the scope of the problem. There's a prophylactic use of the antivirals, and there's a therapeutic use of the antivirals. Right? So if you're sick and you take it, it'll reduce the symptomology, increase your probability of survival, arguably. If you're not sick, it'll reduce the likelihood of you getting effectively exposed, because you have to be exposed longer to actually contract the disease. So it can have a lot of effect on the epidemic curve. So you have to figure out how to balance therapeutic and non-therapeutic use of the antivirals. You have to give them to the right people. So you put these things out. So we're going to also use the market. So you have to know what to give away. So it turns out, I'll just tell you, the end of the story is this, is that you give, if somebody shows up at a clinic or a hospital and they're sick, they're a public health hazard, and you give them the antiviral. You also go to their one diameter at work and home, and you give those people the antiviral, and that begins to balance a little bit between therapeutic and non-therapeutic use, because some of those people are sick and some of them aren't. And then you sell the rest. The consideration on the people that sell the rest is you have to design the market, and you have to understand, so there's a fear and information network that people are plugged into, so you have to figure out how to distribute the information that they receive about the epidemic. They get some of the information by looking around and knowing, some of it by knowing with their eyes. Other times they know by what you tell them. It changes what they're willing to pay given how many people are in their house, the price, and so on. So you can control the price through various kinds of regulatory controls on the market, and you can mess around with gaming and stuff. And at the end, you can calculate what it does to the epidemic curves. And so the optimum setup is the one in the lower left, where it decreases the curve a little bit, but what it does is it pushes it back so there's more time to develop an efficacious vaccine. So the hope is that if you push it back long enough, you can put a vaccine in and you'll never realize the lower curve. Right? So this is, now what's going on here that's coevolutionary is that the price is affected by the demand, which is affected by the prevalence, which is affected by how effective the distribution of the stuff is, which is, and so on. So that the economic decisions and the public health decisions and the health state of the people, and the contact structures that they live in, the dendrograms over those contact structures that the disease is moving over, can't be studied statically. And this is, I'm just going to go on. You don't need any more examples. This is just one that talks about you have a social network that people need to communicate, and then a mobile cell network is affected by that, and so on. So we have the basic elements of simulation, of interaction. I wish my pointer hadn't broken. I'll just do this. You can't read this, so I'll just point. The upper left there is a thing I call an entity, and then to the right is a thing called state. And this is interaction, a state change, a composition of interactions, and system realization. So it's, not super complicated to understand. That's a basic setup for knowing what an interaction is. So in a particle code, you have particles, inertia, collisions, momentum, conservation of momentum, in-body dynamics, but this part's the same. Players, information, action, strategies, individual payoffs. So we can study this piece, and it really doesn't matter if we're studying particles or players or something else if we do it properly. So in studying that on the right-hand side, we have a finite undirected graph Y, which represents causal edges, a sequence of local maps, which is the transition states on each of the nodes, and an ordering of the vertex set of the graph for evaluation. And everything depends on all of those, what the functions are, how they're ordered, and how they're structured over the graph. And it turns out that computers, distributed computers, are also these kinds of things. They're called sequential dynamical systems. And so what you're really talking about is mapping one sequential dynamical system onto another sequential dynamical system, including mapping them onto the computers. And I'm not going to do this. I always put these on here because I feel compelled to talk about them, but I never do. So the fundamental problem of an interactionist representation of this kind, which allows huge speed up and a lot of detail, a lot of control of the model at an individual agent level, is the representation of one graphical dynamical system, one sequential dynamical system by another. And right, so the question of validity of these systems is problematic and interesting, and I'm not going to, we can do it in the questions. Validity always comes up. It came up earlier, and we can talk about it when we get there. Okay, so forget the top. There's work in statistical sciences, network science, algorithmics, all associated with being able to do this and realize it in each of the domain sciences. I mean, there are people that surprisingly think economics alone is enough to do basic research in, or epidemiology alone is enough to do basic research in. That's why there's a lot of research in each of the domains, and there's a lot of applied computer science issues just to get these things to run. There's a lot of stuff like this to make these systems work. The bottom line is what allows them to be fast, well, one of the bottom lines, I guess, is that we don't have encapsulated agents. So there's an agent software object duality that's oftentimes assumed when you say agent. But if you have an agent that's got 2,000 behaviors, making an object heavyweight enough to carry around 2,000 behavioral models is a fairly complicated undertaking. So in an unencapsulated agent, you have dynamical structures in each of the sort of behaviors, which may be in a hypergraph, they may be connected, but you're a trajectory. So what it means is that you're a data library address, basically. You're not a software object. And it allows you to, for example, leave out the stuff that doesn't matter. So the first part of this talk is just about the raw reality of what it means to say we really are in a place where we can compute some awfully complicated things. You know, we've been enabled by big computation to do things that, I mean, it isn't like people just discovered a graph, but to be able to do the things we do, the motif finding, the data search, using it with these very large graphs, this was simply not possible before these big computers. It wasn't possible. Now it's possible, and so these kinds of representations, the practical and theoretical aspects of them are much more relevant than they were before. So the summary is, I've already been through the summary, I don't need to do this. So part 2 is the coevolution of ideas, coupled networks, and mutual thought and action. So we have a system. Here's the system. We have in the world, we have all this unstructured information. We have all kinds of stuff. I mean, anything you can Google, anything you can go find or buy from Dun & Bradstreet or American Community Survey or whatever it is, in addition to all the social media stuff. And it's unstructured in the sense that it was not intended to answer any question you have jointly. It was not jointly constructed to answer any question you have. So it's unstructured data. You have a question, and what we're going to produce is, based on your question, we're going to use this data as it's available, and we're going to produce, using synthetic methods, which I'll describe basically. They use many different kinds of modeling and simulation style methods, but what we're going to do with it is we're going to produce synthetic data structures that allow you to reference your decisions and actions, including what you measure next, to those data structures. And those data structures will be volatile, and they'll be guided by your questions. The next thing is it's focused around figuring out what to do. So the decision support historically is there's a decision. Apparently the world will change as they wish. Well, I don't know if that was ever true, but it isn't true anymore. Stakeholders are much more empowered because of, so we want to build systems that allow access to information, like stakeholders in the decisions that are being made, and all of the stakeholders, including people that make policies, for example, are players in this thing, but everybody has a role. Now you can wish that it wasn't that way, but if what you really want to do is understand what's happening, you have to include the folks and include the level at which they're actually behaving. So we have to go beyond modeling. This is in terms of the kind of things I was talking to you about. It matters what questions they're asking, but that lives outside the computer. That comes with them. So this is an intentional grounding for the system. The people with questions, that's a part of the computation. How they act given the information they get, that's a part of the computation. Sometimes it's computed and sometimes it's not, but if they interact through this platform, then they affect one another through the data structures that they co-use with other people. So, you know, oftentimes we talk about data, we really are thinking about nominal data. We're talking about numerical nominal behavior almost always, not always, but almost always. But there's declarative data. There's declarative data of the kind what but not how, so things that are in statistical fits and things, those declarative information, statistical model outputs are declarative. But there's also procedural information in the world, like how do you drive your car? How do you make a crack cocaine factory? That have a lot to do with understanding what you should see if somebody's driving their car or making explosives or cocaine or buttons or whatever it is that they're doing. Procedural information, like graphs, is something that really hasn't been all that useful to stick together and truly understand in detail how it interacts in detail, really until we had these big computers. And so there's one of the big changes is the uptake of procedural information to allow taking all the measured data that we have and sticking it together in ways that fills in context, things that we can use to guide our actions. I'm going to start with the third sub-bullet there, the size of systems and the size of data. We talked about how much data we're getting. I'll tell you this. With respect to the complexity of the space of the systems we're talking about, I don't care how much data you've got, it's measure zero with respect to what that system can be. Because it's, for example, in no counterfactual world that thing could have generated but didn't. You won't have any data in that counterfactual world. But if you want to understand from a policy point of view how you want to drive something to someplace it isn't, that's exactly what you need to know. So the production of counterfactual information is just one example. There's lots of examples where we can't just say, well, since we have all this data, we can not model so much or not simulate so much, or somehow we're done, we're just generating all this data. The size of these systems is such that it actually doesn't really, the system itself, I'm talking about the structural, dynamical properties of the composed system itself are huge compared to the data, and you must go beyond the data to answer any kind of reasonable decision question for almost any policy question. Now in those systems, because they branch like this, both the forward problem, the reachability problem, and the predecessor existence problem, the inverse problem, unless you apply dichotomies to what kind of rules you're using, the sort of, what amounts to the graph part of the network that you're dealing with, exactly what questions you're asking, in general, both the forward and backward problem are intractable computationally. And they're provably so, and we've had papers out for a long time that have talked exactly about what the dichotomies are that bring these things into any kind of tractable form. And they're very useful when they're tractable, and but you have to be careful. The coevolution piece just causes it to be, all these things to be worse. And I really do think the end of the great man theory of decisions is upon us. And you can disagree with that, but I just can't see how you can disagree with it very strongly if you look at the way things are going on so many different levels. So we want to build a synthetic information platform.
Could you explain that a bit more?
Right. So okay. So we can decide in a fairly minor but large scale example. We can decide to make vaccine distribution a matter of policy. But because of a lot of reasons, it's not simply sufficient to get a probability of compliance with that policy to understand in detail the distribution of the vaccine. You actually have to include, if you want to affect how these people are, for example, not taking the vaccine. You have to understand what information they have access to and how they're using that information to come to that conclusion in the first place. They're stakeholders in an overall, in this case, a public health event, but they're also stakeholders in the outcome of the way that these models or whatever would predict what's going on in the actual world. You have to include, however much you might disagree with them, you have to include them or you can't understand how the system goes. And so just deciding that you want the policy to be a certain way and putting in some sort of abstracted externality that says, well, 12% of these people are going to comply or something is simply not enough to actually understand the system. Yeah.
Are you also including the other way around in the sense of, do your systems contain the reaction of, say, the general public to the policy?
Yes.
So
Now, the general public is
policy as part of the system.
Yes, actions, so that's an important aspect of this, and thank you for that. Is your actions change the information. You see? And so, in fact, in a couple of slides, this is, so how do we go just beyond models? Because we're talking about, essentially, we're talking about intentionally, I mean, in the sense of, I mean, semantics, intentionally grounding these systems in the people that use these systems. It's a human computing style relationship. You're saying, I don't know where you got that question from, but that's your question. It came from somewhere, but I'm not computing that piece. I'm letting you ask it. I mean, this is a stupid example. There's more interesting ones. I just can't think of a single one right now. Okay, but it's a, or how you interpret this and decide what to do. I mean, we'll give you outputs. We'll give you, you know, fictive worlds to look at combinations, but at the end you do something, and that's what gets picked up in the actions that you take. So yes. So stakeholders are part of the system, not just a part of the social system. They're part of this thing which is insinuated into the social system, otherwise they can't measure it, but by measuring it, arguably in many circumstances will actually change it. Sometimes that's a good thing, sometimes that's not. I don't know. But there's no single decision maker or no, you know, there are people that are, they're given authority to make certain kinds of decisions. That's undoubtedly true, but it is not clear what the effect of those decisions are without insinuating the system, insinuating the analytical system, the informatics system inside the social system, and just producing, the word that I'm using is an interactum. I mean, this is a new interactum. It's not particularly new to say that, I suppose, but so if we're not supporting a decision maker, what we are doing is providing a pervasive synthetic information system, and by synthetic information, the focus is taken off the models and into these synthetic information resources, which are accessed like data libraries. When you ask a question, if you say, if you're a public health planner or a person that wants to know if their child should go to school, or anybody associated as being a stakeholder with an outbreak of flu in the flu season in Los Angeles, say, if you go to the system and you say, you ask some question, it's about, you know, like how many children are sick today in this school, or, you know, should I get my child vaccinated today, or would it be okay if I vaccinate them next Monday when it's more convenient, or something like that. These are the kinds of questions you want to ask. Well, lots of people ask this question at the same time, and what happens is at least things like the population, the relevant population representations of Los Angeles wind up getting built by the system. The way the system works is when you ask a question, if you ask a question about Los Angeles, it'll immediately try to build a model of Los Angeles. Now, if it has the population, it'll just pick it up and use it. If it doesn't, it goes and builds one. So if lots of people are asking questions about it, it speeds up with respect to each of the query people. So it tracks, that's, again, a fairly simplistic example. So you're interacting through the synthetic data resource, which is best thought of as layers and layers and layers of networks that are connected by these trajectories, which are you, or this building, or something. Okay, so how do we think about this? How can we think about this? Or what's a forward pointer for how to get our arms around this? So the system itself winds up having a predisposition, I just said, a performance predisposition for certain questions, certain classes of users, certain issues. In every respect, it comes up to be something like a mutually cognitive state among individuals that may not really know very much about what each other have to do with it. I mean, our neurons don't know what thoughts we're thinking. I mean, there's any number of examples. The frog that looks like a leaf, so the bird won't eat it, doesn't know it looks like a leaf. There's all kinds of things like this, right? But to get to this, and this is where the actions apply. It's decisions and actions. What happens is, if you think about this, and how you think about the models, how you think about where the information is, and why it's insinuated in the population. So just if you don't know what extended cognition is like, Andy Clark and David Chalmers a few years ago, 10 years ago, I guess, started talking about the principle of extended cognition, or an idea of extended cognition, and it's sort of been beaten to death and turned into some stuff that's really hideous, but the core idea is really nice, and they've, I think, corrected the more egregious deviations from sanity, but it revolves around a notion called parity. And it amounts to deciding what's cognitive. And I'll explain that, and then I'll say what it has to do with this. So the example they use, I don't know if this is, I'll just make this example. Suppose that I ask you to go to the library and get a book. So the cognitive process initiated in you associated with that has to do with knowing where the library is, knowing how to get to the library, knowing books are in the library. So there's all standard kinds of cognitive things going on. There's memory stores, there's operational memory, there's declarative memory, there's all these kinds of things that constitutes cognition, and you can make a cognitive process representation of what that is. Suppose now, instead of remembering where the library was, you had it written in a little book that you kept in your pocket, and it had a map and stuff. So instead of remembering it by addressing it in your brain, you looked at the piece of paper. But the process flowchart didn't change at all, just where the information was stored. Now, this is a simplistic version of this notion, but if it was cognitive before, it still is the argument about parity. That's why it's called parity. Well, you can extend this then. You can say, well, if I had a process that I could do, but instead I ask you to do it, or if we're jointly engaged in something that you're doing a part of it and I'm doing a part of it, but it results in an information transformation and a connection with both intent, observed data, and behavior, then these ideas of extended cognition apply to this notion of stakeholders interacting through this interactum jointly and affecting one another. So instead of necessarily calling it extended cognition in quite the extreme sort of way that some of the folks that follow Clark and Chalmers have done, we can at least point out that oftentimes you're a part of an overall trend, say, that you don't really even necessarily understand you're a part of, but you are a part of it nonetheless. So that's the first piece. The second piece that has to do with mutual cognition, decisions, and actions is that counterfactual reasoning and scenarios are extremely important when the state space, when the phase space of these systems is so large. So there's work in neurobiology, in this neuroeconomics sort of stuff that clearly shows the following things. So you can, if I put you in a game where I let you bet, and you win, we can identify certain kinds of patterns and locations if you're using an fMRI style thing. I don't want to take it too far here, but you can identify correlated events with reward. And they're associated with dopaminergic systems and all kinds of things. On the other hand, if I put you in a system where I give you a timeline, what I've done is I've extracted a timeline, a price timeline, multiple price timelines. And I give you $1,000 and you're a student. And I let you bid on these stocks and sell these stocks. And I only show you the timeline up to a certain point, then you make your bets, and then I show you the next point. So it could be that you have $1,000, you bet $2 on some stock, and it went up 80 times. So you get rewarded because you made a lot of money on your $2 that went up 80 times. But the problem is if you had put the whole $1,000 on it, you really would have made a lot of money. And you can also find associated events, neural events associated with punishment. That is to say, regret. And so these are called regret mechanisms. And it involves the use, when you have limited amounts of information relative to the total size that the system could be, using counterfactual models, using scenarios about possible worlds, helps you extract learning information from a limited data set. So, the fact that these folks can produce and operate in counterfactual worlds in scenario-driven ways, one of the things I didn't say here is, how do you ask a question? I implied these were simple questions. They're not simple questions, and in fact what normally doing is creating, the interface creates a scenario. It actually creates a space of scenarios. Those scenarios give access to intention, the semantics of the question, through the queries, the actions, and so on. So you wind up with the social cognition style environment, and you can include things like crowdsourcing the information uptake mechanisms and other kinds of human computing issues. So in the platform, intrinsic to the use of the platform and the details of the synthetic information stored, you have an idea, you have represented a system that manifests a mutual cognition platform. Extended cognition is sometimes called out-of-the-head theories, and that's why I said out of our heads. And the other reason is these systems are so complicated, you really can't think about them without, you can't think about them effectively in detail without these sort of informatic aids, but you certainly can't, you can't integrate yourself with all these other people without them. Okay, so the point we are at, we don't understand exactly how these things are playing out, but it's not science fiction that they're occurring inside the synthetic data resources that are being generated by these people interacting. So you ask your question, you take an answer, you take an action, you and everybody else, it's on a global scale, and it changes what you think is important. And if you recall this thing unfolds as you go, so there's the policy question and there's the event tracking question, and they're different. Okay, so I've talked about modeling, and I've talked about the insinuation of these kinds of systems as informatics systems in populations of interacting individuals that are using them, and doing it on purpose so that you actually get this trace and you can measure them, and you can seek to understand them in terms that are explicitly cognitive or explicitly like a model, except they're these people are in them. But I'd like to make some grand challenge statements now about why bother with any of this, and how do you know something's working, and any number of sort of questions like this that a person would be legitimate to ask. So one grand challenge is the classical sort of grand challenge that we have to deal with all the time because of the way we run our enterprise is everybody's not a computing expert, and everybody doesn't have their own high-performance computing system. So this platform is a grand challenge. How do you deploy pervasively so that somebody in Mongolia, somebody in Africa, somebody at MIT can all have access to a system like this? How can that happen? Another grand challenge is this idea of genomics to populomics to sociomics, understanding with the structural properties through synthetic generation and extraction of relations, connection, continuous insinuated connection with the populations are. It's a grand challenge. They're important, and we actually are concerned with them, but they sort of fall short of urgency. And the one I brought up in June, and hasn't gone away, it's still here, is that this is a grand challenge that really does talk to the idea of need for this kind of system. And I'm mindful of, I've got about 3 minutes left here. So in the next 30, 40 years, the population of the Earth, the urban population on Earth, will double. And most of the people that, current trends, given current trends, these cities, it isn't like Amsterdam's going to get really big, and Paris is going to get really big, and New York is going to get really big. These people are in Central and South America, Africa, Sub-Saharan Africa mostly, but elsewhere, Central Asia and South Asia. The cities that they will live in don't yet exist. It takes 40 years to build a subway system. So how do we build these thousands of cities for these billions of people in 40 years? Is a problem that classical urban planning and modeling for urban planning and so on just is silent on. It has absolutely nothing to say about this problem. So I would argue that to engage it by deploying a platform and layers and layers of stuff, which I don't have time to talk about, but I'd be happy to argue about later. We're stakeholders down to the guy who's like, you know, the mud house and a stick. He's a stakeholder with a cell phone or 3G phone or something. If we can build a system that they can engage in, we have a chance to muddle through this problem and not just commit a genocide. So these are the kinds of systems. There's other systems. There's economic planning systems. There's all kinds of systems like this. There's just typical business planning, you know, make your business survive questions that are usefully handled in this kind of way. There's a lot of government policy questions that are handled. But this one is one that really does argue for pervasive deployment, very low levels of, you know, the impedance to access to this thing has to be set very low. And these ideas will come into play to make this sort of thing real. We're not going to be able to sit around and model our way into the solution for this problem. We're going to have to build a platform that allows us to muddle through this thing, and it will use models, it will use all this kind of technology, but it isn't going to be something that we sit in a university and tell them how to do. So the bottom line is here is that ultra large scale, pervasive, participative synthetic informatics systems can change everything.
We have time for -1 question.
-1. Chris, question. Can you say something about economics of building such models? How does it scale as you go into the different scales of number of independent agents, and what sort of man-year efforts to model a whole city, for example?
Right, I actually have, so as you build out, okay. So we have designed these systems. So when you go into a new area, it's pretty labor intensive to build the environment for the new area. And it takes a while to build out the new area. So in this thing that now runs in half a second that used to run in 48 hours, the development time has gone from 6 months to about 20 minutes to set up the models.
Oh, that's good.
So these things are connected. And it's connected because as you build these tools, you wind up with meta tools basically in domains, and the users of the tools can do it themselves. I mean, not very long ago, to query a database would require that you made your own database query tools. But you don't do that anymore. Somebody else built those tools and you use them. So it's yeah, pervasive access to high performance computing is changing very quickly.
Basically, it's very doable.
Yeah.
Okay, many thanks.